In the last video, we discussed the substitution technique for integration. This technique is used when we're integrating a function that resulted from differentiation via the chain rule. So in this video, we're going to talk about another integration technique referred to as integration by parts. So integration by parts will allow us to integrate another set of functions, specifically functions that resulted from differentiation via the product rule. So just as it was important to understand how differentiation looks when we use the chain rule, the same applies when we're talking about the product rule. So suppose we took a product of two functions, u and v, each one of them is a function of x, and differentiated their product with respect to x. Well, we know that we take the first function times the derivative of the second function, so that would be the derivative of v with respect to x, and then we add on the second function times the derivative of the first function, which would be du dx. So for any functions u and v associated with the variable x, if we want to differentiate their product, this would be the formula we use. And as we know, anti-differentiation reverses differentiation. So if the idea is that we're given something of this form and we want to take its antiderivative, well then it will anti-differentiate, integrate back to the original product of two functions. So suppose we were to integrate both sides of this equation with respect to x. So we integrate d dx of uv with respect to x, okay? And that would mean, of course, anti-differentiating the other side as well. And we know we can take an integral term by term. That was one of our rules for integration. So we're also taking the antiderivative of u times dv dx with respect to x plus the antiderivative of v du dx also with respect to x. So at this point, it's really just a matter of how do the integrals affect the derivatives. So in the case of the left-hand side of the equation, we have an integral of a derivative. So literally, those are inverse operations. They cancel one another out. You can think of it as the dx for differentiation, eliminating the dx that is associated with integration. Well, this dx, this differential, goes together with the integral symbol. They kind of are sandwiched together. So if this dx completely goes away, then integration is no longer present, which means on the left-hand side, we're just left with uv. We can't have the integral symbol without the differential, so we're just left with the original function. Now, what about the other side? Well, for our first antiderivative, we have a matching factor of dx that divides out. But notice we haven't completely eliminated a differential. Now we just have a new differential. We have the differential of v. So we still have an integral, but it's now the integral u dv. So it's no longer integrated with respect to x. It's integrated with respect to the variable v, which is associated with one of the original functions. Now similarly for the other one, our dx is eliminated, and we're left with v du. So we still have an integral, but now we're integrating with respect to u, which is associated with one of the other original functions. Well, what are we actually interested in when we use integration by parts? Because based on looking at this, it seems like if we want to use integration by parts, which supposedly just takes the product rule and reverses it, then it's really routine. It's just taking the antiderivative of three individual terms is what this looks like. What we're actually focused on is one of these two integrals. So suppose maybe just this one integral. So imagine that the integral u dv is what we're actually interested in integrating. So some function multiplied by dv, the differential with respect to another function. In other words, non-matching variables. Suppose this is the actual integral that we're trying to find. Well, based on its relationship in this equation that resulted from integrating the product rule, we can solve for it in terms of the other two terms in that equation. So that means that u dv would be the same thing as uv minus this other integral. So all we're doing is rearranging the formula we get if we take the antiderivative using what we resulted from the product rule for differentiation. This is what we refer to as the integration by parts formula. So the idea is we have a function that is a product. We have an integrand that is a product of two functions, and at least one of them can be integrated using techniques that we've already seen. So what's the goal here? The goal is to take something that's a product of two functions. U is one function. dv is another function that will also involve the differential. It'll involve a differential. So dv is going to be a standalone function and a differential. But think of this as the challenging integral. This is the one that we don't currently have a technique to solve for. Okay. But if we can use this formula to rewrite it in terms of just two individual functions, no differentials involved, and another simpler integral. Think of this as a simpler integral that's generated from the information we get from our original integral. If we can take this more complicated integral and break it apart in such a way so that the two functions involved will allow us to create a simpler integral. This integral will be one that we can solve for directly, one we can find directly. Then that's how this formula is going to work. So the integrand, what we're integrating, is a product of two functions. At least one of them can be integrated using the techniques we already have. So essentially what we then need to do is we need to determine which function is going to work which way, because again, u will be a standalone function, and then dv will be a standalone function that also has a differential associated with it. So u is going to be f of x, okay, some function f of x. Specifically, we want to choose f of x where f of x is a function that can be differentiated. And that's not difficult to find. Pretty much any function, we can differentiate it. But typically, we're going to pick some function where we differentiate it, and differentiating it makes it simpler. It doesn't make it more complicated. So we want to find a function where if we took its derivative, in most cases, the differentiation is going to take the original function and it's going to make it simpler. Now, dv is the other part we have to determine in using this formula. dv is going to be another standalone function plus the differential with respect to x. And specifically, we want to choose g of x, where g of x can be integrated. And this ultimately is going to be the more important choice of the two. So we have to find a function that can be integrated as a standalone function and integrated in such a way that it's not going to become overly complicated when we integrate it. Now, this is one of those techniques that definitely just takes some practice. I want to emphasize right now that finding the right pair, finding the right value of u, the right value of dv, again, u is one function involving x, dv is another function involving x associated with x. U is going to take on the value of a function that can be differentiated, and dv is going to take on the value of a function that can be integrated. Finding the right pair that's going to work and that's going to result in, again, another integral, a new integral that is simple enough to integrate using just the techniques we already have. This is challenging. This is a challenging technique to use. And again, I want to emphasize now, it's going to require some trial and error. In a lot of cases, you'll pick a pair that originally seems like it could work. You differentiate one, you integrate the other, and yet somehow it makes the problem more challenging and you get stuck. That means more than likely that's not the pair that you need to choose in order to use this particular technique. So it's going to take some trial and error in order to figure out which function is going to be which part, which function is going to be the other part. And don't be afraid of just trying some different combinations. If you find one that doesn't seem to work, try a different combination. There will be a combination that works, it just may not be the first one you pick. So we're going to do several examples. It's again just kind of like substitution, it's just a repetition kind of thing. We need to see this over and over. We need to see the general strategy for choosing each part, choosing your u, the function you differentiate, and choosing your dv, the function you integrate, in such a way that they combine to give you something simpler when you write this new integral. So we're finding this integral related to two functions u and v. They're going to be functions in x, also associated with another integral that will be simpler to evaluate. So rather than evaluating this integral directly, we're going to break it down and write it in terms of a product of two functions and then a simpler integral generated from how we find u and how we find v. Okay, so let's just try an example, and we're going to start with a relatively basic one and then we'll build from there. Okay, so we want to evaluate each indefinite integral by integrating by parts, and if necessary, just try different combinations of u and dv. Okay, so our first function that we want to integrate is x times e to the x, integrated with respect to x. So first off, this is not a substitution kind of problem. So remember, when we looked at substitution, the idea was we have an outer function and an inner function. And whatever our inner function is, we also see its derivative in the problem. Well, there's no clear nested function here. And if we thought of maybe x as a function, we need its derivative in the problem, which would just be 1. Well, where does that leave us with the e to the x? If we have the e to the x and let it be the function that we substitute for, well, we need to see its derivative there, which would be another e to the x. Well, where does that leave us with the x? Ultimately, this is not the kind of function where substitution is going to help us. This is the kind of function where we use integration by parts. Think of it as two standalone functions, a product of two functions, standalone, individually, where they're not related to one another in terms of how the derivative might be associated with one or the other. So what do we need to do? I'm going to write down the integration by parts formula so that we can work our way through the different parts of this procedure. So we have the integral of u dv is equal to, just rearranging the product formula as we saw a moment ago, is equal to uv minus the integral of v du. So think of this as the problem we're trying to solve. This is the integral we have right here, right now. So one of the functions will be u, and then one of the functions combined with the differential will take on the role of dv. And so based on the choices we make, we're going to find u, we're going to find v, we're going to find all the different parts. So whatever we choose to be u, we also need to find its derivative, and whatever we choose to be dv, we have to find its integral. So we have to find all these functions, we have to find their derivatives. And again, the goal, the ultimate goal here is to pick the right combination of u and dv, where when we plug into this other integral using the values we've chosen and found, we end up with an integral that's more straightforward to solve than this one where we don't currently have a technique for solving it, evaluating it directly. Okay, so how do we pick u? How do we pick dv? Well, again, u is going to be integrated. So we're starting with a u. We're going to, or not integrated, excuse me, it's going to be differentiated. It's going to be differentiated in order to give us what we'll call du. And dv is going to be a function plus a differential that we're going to integrate to find v. Okay, so think of u being something that we differentiate, dv is something that we integrate. So ultimately, we need to find something that can be differentiated and then something that can be integrated by itself. Now there's two different pairs that might work here, and I want to look at them both and we'll see which one is going to help us out. Okay, so how would we potentially choose one versus the other? Well, one way we could choose u. Suppose we want u to just be a function of x. Out of the two that we have x as a function of x, we have e to the x as also a function of x. So one choice we could make is that u is just x. Okay, it's just that. So that's the value that u is going to have. That means automatically that dv would have to be everything that's left over. So dv is going to be another function of x plus the differential. So if we allow x to be u, then that means everything left over is going to be dv. So e to the x, which is a function of x, times our differential dx. Okay, so based on this choice, we now need all the different versions of u and v so that we can find the other two parts in this formula. So we have u, we have enough to plug in right here, and we have dv, which means we need now a little bit more. So we have u, we can plug in directly for u, but we need to find v, and we also need to find du. Well, if u is x, we can find du. Du is going to be the derivative times dx. So let's maybe take it one step slower. So remember when we use substitution, if we wanted to find just one differential, we took the derivative, so the derivative of u with respect to x, in this case, is going to be the derivative of the other side as well, which will just be 1. So that means du is just going to be dx. Okay, so that gives us u, which we would sub in here, and that also gives us du, which we would sub in here. So what about dv? Well, if we have dv, think of it as that being a derivative. We have a derivative, okay? So in order to find v, we would need to find its antiderivative. If we have a derivative and we want the individual original function, we find its antiderivative. So that means that v is going to be the antiderivative of e to the x times dx. Well, we know how to find that antiderivative. We know that it's going to be its own antiderivative, so it's going to be e to the x. So this we can now substitute in place of v, right there, and right there. So once we have our u, we have our du, we have dv, we have v, we have everything we need to use the integration by parts formula. So this is our u dv, okay, this is what we're trying to find, and now we're writing it in terms of the formula on the other side. So what's it going to be based on this choice of u and this choice of dv? Well, it's going to be u times v. Well, what would that be in this case? Here's our u is going to be x, and v is going to be e to the x. So it would be x times e to the x. Okay, minus the antiderivative of v du. Well, v is e to the x, and du now is just dx. So we now have a product of two functions that we can leave alone, plus an antiderivative, or rather minus an antiderivative that we're intended to evaluate. And this needs to be something we can evaluate directly. And fortunately, we can now evaluate this directly. We know what the antiderivative is of that function. So the antiderivative of e to the x is itself, it's e to the x. And so we take that antiderivative and then we add on c. And that's it. That's our final answer. That's all we need to do. So we took this more complicated antiderivative and we broke it down in such a way that we could evaluate a simpler antiderivative that's sort of related to the original. It's related using the u to du and the dv to v relationship. Now, I did mention I want to show you two different ways that maybe you could come up with values for u and v, where one works and maybe one doesn't work as well. So again, what are we choosing? We're choosing u to be one function involving x, one of the two functions, and then dv will be the remaining function and the differential. So this first choice, we allowed u to be x, and then dv took the remaining function of x plus that differential. Well, what's another way we could have chosen values? Well, suppose instead of letting u be x, maybe we let u be e to the x. Again, what is u going to be? It's going to be something that we can take the derivative of. Okay? So that means dv is going to be everything else. So it would be the remaining function of x, which would be x, and the differential. So based on the original problem we have, this would be another pairing that we could choose for u and dv. And again, once we make that choice, now we need to find the remaining parts that we would need in order to use the formula on the right-hand side. So we have our u, now we need a du, and we need our v from our dv. So if we want du, we need to take our derivative of u, which is going to be e to the x, and so du would be e to the x dx. Okay, so we know what we'll substitute in place of du. Now what about the other side? Well, dv means we've been given a derivative, essentially. So if we want to find v, we have to integrate it. So that means v is going to be the antiderivative of x with respect to x. Okay, so this would be a power rule problem. So increase the exponent and then divide by that new exponent. So v would be 1/2 x squared. And now we have everything we need. So we have u, du, dv, and v. So we have enough to use the formula. But now we're using the formula not with this combination of values, but with this combination of values. And the goal is to compare and see what would happen if we use this original assignment rather than this original assignment. So I'm going to plug in u and v. So here's our u, and here's our v. So rewriting them, going ahead and rewriting them in a slightly different order, we'll say 1/2 x squared times e to the x. That's the standard order if we've got something that's exponential plus a constant plus something that's polynomial. So constant, polynomial, and then exponential. So uv, just rearranged a little bit, minus v du. So v is going to be 1/2 x squared, and then du is going to be e to the x times dx. Okay, so now we're right where we were here. The goal is to evaluate this antiderivative. But if you look at this antiderivative, what we're now supposed to evaluate, it's actually more complicated than what we originally started with. This is a more complicated antiderivative. You can probably just tell from looking at it. Instead of just having an x, well, now we have an x squared, which is automatically bigger. It's more complicated. It's more of a problem. This is more complicated than the antiderivative we started with. So this particular combination of assignments allows us to find different parts. We can differentiate, we can integrate, we can find the original parts. But the new integral we generate is actually more complicated than the one that we started with. So because this pairing leads us to something that's more complicated than what we started with, something we can't integrate directly, then that indicates that this would not be the pairing we would want. We would not want u to be this function and dv to be this function times dx, because it leads us with something that is more complicated to solve. So because this integral, we don't have a technique to solve, this would not be the pairing we want to choose. This would be the pairing we want to choose. Because again, once we got down to plugging things into our formula, the new integral we generated was one that we could find. It was one that we could evaluate using the techniques we already have. So we lucked out in choosing the correct pairing first. But what if we'd chosen this pairing first? Well, it just means we would realize once we got to this point that we were still stuck. It means we didn't pick the right pair. So then we go back to the drawing board and we try another pair. And again, that's perfectly fine. Trial and error is normal with this type of technique. So once you do enough problems, you'll start to recognize some specific pairs that just seem to work in terms of choosing one to be u and one to be dv. But if you don't, again, if you never get to that point, that's okay. It's just a matter of understanding that trial and error is a necessary part of the process and accepting it and recognizing how you can choose different values of u and different values of dv. Okay, so let's try another one. And again, accepting that maybe we pick a pair the first time and it doesn't work. Maybe it does. Maybe we luck out. But if we don't, it's okay. We just try something else. Okay, so we have the natural log of x, and I want to emphasize this is not a product of any type. This is a function with x plugged in, times dx. Well, this is different than the one above. The one above, structurally speaking, was very much a product of two things. X was a function involving x, e to the x was also a function involving x, and then we had our differential. And that's what we normally see when we use integration by parts. Because it comes from the product rule, we typically expect to use it when we're looking at a product of two functions that we're integrating. Well, here we don't have an obvious product of two functions. If we were to think of this as a product, the only way to think of this as a product is to think of ln of x as one part and dx as another part. Now we could also think of there as just maybe being a 1. If we wanted to add in another function that's multiplied in all of this, we could add in the function 1. That's certainly a possibility. Okay, so the goal now, regardless, is we're going to have to choose our u, we're going to have to choose our dv. So let me write down the formula again. So we have u dv is equal to uv minus the integral of v du. So this is the problem we're solving, and this will be the formula we're using. And again, the idea is we want to take this integral, which we can't find directly. Why can we not find this directly? What's the problem? Well, we don't actually know what the antiderivative of the natural log of x is. We know its derivative, but we don't know its antiderivative. So we're using this formula to take an integral that we can't find directly and maybe write it in terms of an integral that we can find directly. Well, automatically, I just gave you a clue for how we're going to pick what u is and what dv is. So remember, the rule with u needs to be something that we can differentiate, and dv needs to be something that we can integrate. If they were just standalone functions, u is something we can differentiate, and dv is something we can integrate. Well, as I just mentioned a moment ago, natural log of x is not something that we can just directly integrate. If we could do this problem right now. It's not something we can integrate. So that means natural log of x is not going to be assigned the role of dv. It's not going to be part of dv. That means it has to be part of u. That's the only way we can use integration by parts in this situation. We can differentiate natural log of x, but we can't integrate it. So I'm going to allow u to be natural log of x, knowing that I can differentiate it, and when I differentiate it, I know I make something simpler. When we take its derivative, we get 1 over x, which is simpler in some ways than the natural log function, which is a special function. Now once we choose u, automatically that means dv is whatever is left. Well, what's left if we've already chosen the natural log of x? What's left is dx, which looks like maybe we don't have enough. So if it helps, think of it as 1 dx. 1 is our function, and then dx is our differential. So now we have something that looks like we actually have a function to integrate. Because again, what do we need? Well, we have u, we have dv, so we have everything we need right here. We have our u, but we need v and we need du. Well, we get the du from differentiating our u, and we get the v from integrating our dv. So let's do that. So we need to differentiate our u, we need to integrate our dv. So if u is equal to the natural log of x, then du dx is equal to 1 over x, and du, what we're really interested in, is equal to 1 over x times dx. Okay, now dv, we have to integrate dv. So that means v is going to be the antiderivative of 1 times dx. Well, this is technically still the power rule. Think of it as x to the 0 power. If we have 1, we really have x to the 0 power. So increase the power by 1 and then divide by the new power. which is just going to leave us with x. And so now, potentially, we have a pairing that will allow us to use the integration by parts formula. So we have our u, we have our du, we have our dv, we have our v, we have everything we need. So here's the problem we're solving. This is our formula that we're going to substitute into in order to find it indirectly. So our uv, well, our u is now the natural log of x, and v is x. So the standard order there would be x times the natural log of x, just so that it's clear that they're multiplied and that it's not two x's inside our natural log. And then we are subtracting the antiderivative of v du. Well, v is now x, and du is 1 over x dx. And again, what's the goal? The goal when we use this formula is for this new integral to now be simpler, to be one that we can solve for directly, whereas the original one was not one that we could solve directly. Can we solve this directly? Well, notice what happens once we made that substitution. That x now completely goes away because it's a matching factor on top and on bottom. So what we're actually left with is x times the natural log of x minus the antiderivative of what? Of just 1 dx. And that is really basic. That's one we can actually do just using what we know about our standard antiderivative rules. And so when we take the antiderivative right there, we still have our x times natural log of x, but the antiderivative of 1, we actually just did that one. It takes us to x, so it's minus x, and then plus our constant of integration. So that is going to be our antiderivative. Okay, let's try another one. Step it up a notch. Okay. So now we've taken the natural log function, but we've multiplied it by another function, by x. So we have the antiderivative of x times the natural log of x. Now again, substitution is not a good option here because we don't have a function and its derivative present in this problem. If we wanted to think of natural log of x as what we'd substitute for, well, we'd need a 1 over x. We don't have a 1 over x in this problem. So substitution is not an option in this case. So integration by parts is a good option because we see a product. Potentially this could relate to something involving the product rule. So here's our formula again. We're anti-differentiating u dv. This is going to be our u dv. And that's going to be equal to uv minus the antiderivative of v du. So based on our choice of what we're going to allow to be u and what we're going to allow to be dv, we want to generate a simpler integral that we can find directly. Okay, so we now have a product of two functions, so more than likely we're probably not going to want to use the same approach we used right here, where u was just the function itself and then dv was just the differential. If we took that approach, then we would allow u to be x natural log of x, the whole thing, and then dv would just be dx. The problem with maybe taking that approach is if we allow this to be our u, then when we take its derivative, that would use the product rule, which means we're going to end up with a complicated derivative. The goal is for the differentiation and the integration to lead us to relatively simple functions, not more complicated functions. So what's another pairing we could use? Okay, so we need a function that we can differentiate. That's going to be our u. We need a function that we can integrate. That's going to be our dv. So a function that we can differentiate. Well, we can certainly differentiate x, but that would leave us with natural log of x, which we know we can't integrate directly. So maybe go the other way around. So what if we let u be just the natural log of x, which we know we can differentiate, and we'll let dv be x times dx. which we know we can anti-differentiate. Let's see if this pairing works for us. So u is natural log of x, dv is x dx, so I need my u, which I have, I need my v, which I'll get from anti-differentiating, and I need my du, which I'll get from differentiating. So du dx is equal to the derivative of natural log, which is 1 over x, and then du is equal to 1 over x dx. Okay, so we know what we are du. And then for dv, we need to integrate to get v. So v is going to be the antiderivative of x with respect to x. And we know that's going to use the power rule. So increase the exponent, divide by the new exponent, and we get 1/2 x squared. So we have our u, our dv, our du, and our v. So let's plug into our formula and see what we get. So here's our u dv. It's equal to u times v, so natural log of x, times 1/2 x squared. So written in the more appropriate order, that's 1/2 x squared times the natural log of x, minus, here's the important part, we need for v du to be something that is now a simpler integral than the one we started with. So v is going to be 1/2 x squared, and du is going to be 1 over x dx. Well, before we decide whether or not that's an integral we can actually evaluate directly, let's simplify this a little bit. So focus on the x's. Notice we have an x squared, which would be part of the numerator, and then we have an x in the denominator. So if we cleaned that up a little bit, we still have our 1/2 x squared, ln of x, minus our 1/2, and then x squared on top and x on the bottom is just going to leave us with an x dx. And sure enough, this is now something that we can integrate directly. We can integrate this directly just using the power rule. So either we can go ahead and pull the 1/2 out if we want, or if we know what to do with the exponent once we get it, then we can just go ahead and leave the 1/2 and go from there. And I'm going to do that. So we have 1/2 x squared, natural log of x, minus 1/2 divided by our new exponent, which would be a 2 times x squared plus c. And then let's just clean that up, combine those together. So division by 2, that would be the same thing as multiplication by 1/2. So we have 1/2 x squared times the natural log of x minus 1/4 times x squared plus our constant of integration. So that would be our antiderivative in this case. And again, notice the choice we made was dependent on finding something that we could differentiate. Natural log of x could be differentiated, as well as something we could integrate. X dx was something we can integrate. Now, just for the sake of showing you what would have happened had we attempted a similar strategy to the one we had on the previous example, what if we picked a different value for u and dv, just to see what happens? So remember, for the previous one, we just allowed u to be the whole function, everything involving x, and then dv was just the differential, which we could think of it as just 1 times that differential, if it helps. Suppose we made that kind of attempt here. Let's see what would happen. So if we allow u to be the whole function, the product in this case, which would be x times the natural log of x, we can pick pretty much anything we want for u, because the only stipulation for u is that it needs to be something we can differentiate. Well, we can differentiate pretty much any function we want using our product, quotient, and chain rules. So we can find this derivative. So that's a reasonable choice for u. Now that means in this case that dv would have to be dx, and we know it needs to be something that can be anti-differentiated. And sure enough, we just saw from the previous example, think of this as like a 1 dx. We can take its antiderivative, so that is an okay choice for dv. Ultimately, the question, though, is if we make those specific choices, are they going to lead us to create a new integral that's easier to solve than the individual original one? That's the question we have to answer. So we'll answer that by finding the other parts that we'll need. So du dx. Okay, now this is a product. So if we want to find its derivative, we know we need the product rule. So first function times the derivative of the second plus the second function times the derivative of the first. Okay, and if we clean that up, well, this isn't too bad. A couple things go away. So notice the x's go away. They cancel out. That just leaves us with a 1. And then our next term would just be the natural log of x. So if we wanted du, that would be 1 plus the natural log of x times dx. So now we need to integrate dv. So v is going to be the integral 1 dx, which means it's just going to be x. So with our u, our du, our dv, our v, we now have enough to substitute into our integration by parts formula. So uv, there's our u, there's our v. Okay, so we have x times the natural log of x times x. So x times x, that's going to give us x squared. And then our natural log of x minus our new antiderivative, the one we're really interested in. So v is going to be x times du, which is going to be 1 plus the natural log of x dx. So the focus is now on what do we do with this antiderivative. So let's clean this up. So x squared times the natural log of x minus, if we were to distribute our x, that's going to be x plus x natural log of x dx. Well, what would we do here? Okay, well, we've got two terms. We know we could antidifferentiate one term at a time. So we could take the antiderivative of x. We know what that is. But here's the problem. If we were to look at the next term, it's the antiderivative of x ln of x. Well, that's actually the original problem. That's the one we couldn't actually antidifferentiate directly. That's what we're attempting to find. And suddenly, the substitution we used into the integration by parts formula reintroduces us to the original problem that we were trying to solve that we couldn't solve. So suddenly, we end up essentially right back where we started. How would we find that integral? We can't find it directly. That's the whole reason for using this integration by parts technique. So because this particular pairing then gave us an integral that is no simpler to solve than the original, this particular combination is not going to work. Because that integral is not one we can now directly evaluate, this is not going to be the combination we want. This will be the combination that we want. Okay, let's try another example. So we'll do one more indefinite integral and then we'll look at a definite integral. So we have the antiderivative of x times the square root of 5x plus 1 integrated with respect to x. Okay, so here we have a nested function. So maybe we could use substitution. So the square root of 5x plus 1 is a nested function. Okay, so f of x plus 1, or excuse me, not f of x, 5x plus 1 would be our inner function. But we know in order to use substitution that we need to have the derivative of our inner function as a factor in the problem. So the derivative of the inner function would be 5. Okay, but where does that leave us with the x on the outside? We know when we use the derivative of that inner function that it needs to somehow get rid of that other expression involving x that's outside of the nested function. Well, in this case, that's not going to happen because the derivative we would need on the outside is not there. We have an extra function involving x that's not going to go away when we make our substitution. So substitution, even though it looks like it might apply here, it's not going to apply here. So that's not going to be our option. Our option here is going to be to treat this as a product and use integration by parts. So we're integrating something of the form u dv, and that's going to give us u times v minus the integral of v du. So what's our u? What's our dv? Well, we need to be able to differentiate u. We need to be able to integrate dv. So using the functions we have, one of them is going to be our u, and then the other one paired with the dx is going to be our dv. So first off, which one can we actually integrate? Maybe that's a good question to ask, because again, integration is the harder part. Differentiation we can do pretty much no matter what, but integration not necessarily the case. If I were to just look at the 5x plus 1 square root, I cannot directly integrate that. I would need to use substitution to integrate that. That's going to be a mess to integrate. In theory, we could try it, but what's going to happen if we try it? Well, let's see. So another option, if we let x be u, okay, we could let x be u. Let's just see. Let's try both ways. Let's see what happens. So suppose we let u be x, and suppose we let dv be the integral, or excuse me, the square root of 5x plus 1 dx. Let's see what happens. It looks like maybe it wouldn't work, but will it work? Let's see. Again, trial and error. We try it in the formula. If it works, it works. If it gives us a more complicated integral, then we assume it doesn't work and we go from there. Okay, so if we choose u to be x, we know we can differentiate this. Can we integrate this? Well, let's see. So first off, we know we can differentiate. We'll go ahead and take care of that. So du dx is going to be 1 based on this choice of u. And so du is just going to be dx. Okay, so we know what we'll substitute over there. Now we need our v. So v is going to be the antiderivative of the square root of 5x plus 1. Well, let's write that as 5x plus 1 to the 1/2 dx. Can we integrate this? Do we have a technique to integrate this? Well, we know we don't have a technique involving just a straightforward rule, but could we use substitution here? Well, again, we want to think of it as an inner function and an outer function. Clearly, we have an inner and outer function, and we need to have the derivative of the inner function present in this problem. Well, the derivative of the inner function, 5x plus 1, would just be 5. Well, I don't see a 5, but I also don't see another function here that's going to get in the way. So it looks like maybe we could integrate this just using substitution. You can think of there as being an understood 1 right there. Well, 1 is a multiple of 5, or vice versa. 5 is a multiple of 1. So because, again, we don't have an extra function involving x there, because this derivative is just a constant, maybe we can use substitution. So what happens if we try substitution? Let's see what happens. Now, normally we substitute using u, but we've already used the variable u in this problem. So let's just pick another variable. Suppose we use the variable w. Okay, so we're going to let w be our variable for substitution. So we'll allow w to be 5x plus 1, which means that dw is going to be 5 dx, and dx is going to be dw divided by 5. Okay, so now we have something to substitute both for our inner function and for our differential. So that's going to be the antiderivative of 5x plus 1, which is our w, to the 1/2 power, times dx, which is dw over 5. Well, that 5, we know it's really the same thing as a 1/5. So this is the antiderivative of 1/5 times w to the 1/2 dw. And that we can integrate. So substitution is an option here, and substitution will allow us to take the antiderivative of dv, thereby giving us our v. Now that still doesn't tell us whether or not it's going to help us from the standpoint of integration by parts, but at least it is feasible. It is a feasible option. So I'm going to increase my exponent by 1, which would take me to 3/2, and then I'm going to divide by that new exponent. So I have 1/5 divided by 3/2, and that's now w raised to the 3/2 power. So my coefficient is going to be 1/5 times the reciprocal of our denominator times w to the 3/2. And so we can clean up the coefficient, and then we can resubstitute in terms of x, and that will be our value for v. So the coefficient, numerator is 2, denominator is 15, and then w is 5x plus 1, so that's going to be 5x plus 1 raised to the 3/2. Okay, so we have our u, we have our du, we have our dv, we have our v. Let's plug them in and let's see what happens. And again, it may work, it may not. It's really just going to depend on how the pieces fit together once we start to put them into the formula. So u and v, we can always do that part. So u is x, and this is v. So I'm going to insert that x between the 2/15 and my parentheses. Just go ahead and write it in the standard order. So 2/15 times x times 5x plus 1 raised to the 3/2 minus, here's the important part, antiderivative of v du. Well, here's our v. So we have 2/15 times 5x plus 1 raised to the 3/2, and du is now just dx. So what do we think? Can we integrate this? Well, it looks to me like this is just another substitution problem. This is just substitution again. So we have an inner function and an outer function. We know we can use substitution if we see the derivative of our inner function present as a factor. Well, our derivative for our inner function is just going to be 5. I don't see a 5, but I also don't see any other functions involving x. It's just a constant. And so if it's only constants associated with the derivative, and then anything on the outside that's still being integrated, then we can use substitution. And so we're actually going to substitute the same value here. We're going to use the same substitution. So we're going to allow w to be equal to 5x plus 1. So dw is equal to 5 dx, and dx is equal to dw divided by 5. Okay. So let's just focus on this antiderivative for a moment. We'll worry about this other part in a moment, but just for now, let's just focus on this antiderivative. So we have 2/15 times what we're now replacing with w raised to the 3/2 power. So we have the antiderivative of 2/15 times w raised to the 3/2 power. And we're changing our variable of integration. So dx now becomes dw over 5. Okay, just constants. So now we can combine those constants together. So 5 times 15, let's be careful. So 15 times 5, that's going to give us 75. Okay, so 2/75 times w to the 3/2 dw. And now we can integrate. And if it helps, you can pull the 2/75 out front. Remember, it does not affect our antiderivative. So it's separate from it, so we now just increase our exponent by 1. So 3/2 increased by 1 becomes 5/2, just to verify that. 3/2 plus 1, which is 2/2, is going to give us 5/2. Okay, so our new exponent will be 5/2, and then we're going to multiply by the reciprocal. We divide by the new exponent, which is the same thing as multiplying by that exponent's reciprocal, which would be 2 over 5. And then the last thing we need to do, clean up our coefficient and then resubstitute. Okay, so what's the coefficient going to be? Well, 2 times 2 is going to be 4. What about our denominator? 75 times 5. It's going to be 375. And then W is 5x plus 1. And that's now raised to the 5/2 power. And then we have our plus C. And then don't forget everything else that we had prior to this. So we had 2 over 15 times x times 5x plus 1 raised to the 3/2 power. So very complicated antiderivative, very complicated. But this is our antiderivative, and it resulted from the choice we made for choosing u and for choosing dv. So that is going to be our antiderivative. Now, what happens if we'd chosen a different pairing? So I'm going to flip over. You might want to just grab yourself an extra sheet of paper if you're filling in the notes on the outline. Let's just see what would happen if we tried a different pairing. Because then again, it's worth the practice to see. Because what if this is not the first choice you made? What if you chose to take the other direction? What would happen? It's worth investigating and seeing what we would encounter if we used another pairing. Okay, so I'm going to flip over and I'm going to rewrite the problem, and we're going to do the problem with a different pairing. Okay, so we had the antiderivative of x times the square root of 5x plus 1 dx. Okay, so the original pairing we chose was that u would be x, and then dv, what we would integrate, would be the square root of 5x plus 1 dx. What if we chose another pairing? So what if we looked at this function and said, oh, this is going to be something I can't integrate. Maybe it's something I can differentiate. What would happen if we made that choice? Well, that means we would allow x to be 5x plus 1 to the 1/2, if we want to think of it that way. And of course, we know we need it in that form in order to use our derivative rules. And that means dv would be x dx, which is certainly something that we can integrate. So in some ways, this might be, this should be a u. In some ways, this might be a more obvious choice because, again, when we identify dv, we're looking for something we can take the antiderivative of. This, we know we can take the antiderivative of this, but just looking at the square root of 5x plus 1, does it immediately stand out as something you can antidifferentiate? Maybe not. So suppose this was the pairing you chose, knowing that you could differentiate this and you could anti-differentiate this. What would happen if we took that direction? Well, we would have our du dx. Now, differentiating this would require the chain rule. So we would bring down our 1/2. So 1/2 times 5x plus 1 raised to the negative 1/2 times the derivative of the inner function, which would be 5. So if we clean that up, that's going to be du dx is equal to, combine your constants, so that's going to be 5 over 2, and then our square root will go to the denominator. So that would be 2 times 5x plus 1 to the 1/2, and then we have a 5 in the numerator. And of course, we could rewrite it as a square root if we want, or we can just leave it with an exponent of 1/2, knowing that potentially we'll need that form again anyway. So what we need ultimately is du, though, so that's going to be this expression times dx. So I'm going to write my denominator first, just so I space it out nicely. So 2 times 5x plus 1 to the 1/2 power. We've got our 5 in the numerator. And then we're multiplying by x. So this is going to be our du. So our v is going to be the antiderivative of x dx. So that means v is going to be 1/2 x squared. So we've got our u, we've got our du, we've got our dv, we've got our v. rewrite our formula again. So we know that u times dv, the integral we're looking to evaluate, is going to be uv minus the integral of v du. Well, we know what u and v are. We can substitute for those directly. But again, what's the goal? The goal is to now generate an antiderivative that will be simpler to solve than the one we originally encountered, the one we can't solve directly. So let's see if that is in fact the case. So uv, here's our u, here's our v, so that's going to be 1/2 x squared times 5x plus 1 raised to the 1/2. So that's not a problem, it's just what happens with our integral. So minus v du. Well, v is going to be 1/2 x squared, and then du is all of this with our dx. So 5 over 2, we'll break that apart, and then we have a 5x plus 1 to the 1/2 in the denominator, and then we have dx. Well, just because this looks complicated doesn't mean it can't be antidifferentiated. The previous one looked complicated, but we were able to find its antiderivative. So we really need to clean that up before we make a determination about whether or not we could evaluate that. So we have 1/2 x squared. We have our 5x plus 1 raised to the 1/2 minus, okay, let's combine our constants. So 1/2 and 5/2, that's going to be 5 over 4. And then maybe put the x squared on top and then leave this in the denominator. So that's going to be 5x plus 1 raised to the 1/2 in the denominator. And then we have x squared on top. And then dx. This is maybe a problem. Looking at it in this form, it's probably a problem. So we see a nested function. Okay, we see 5x plus 1 raised to the 1/2. We could think of it as being raised to the negative 1/2 since it's in the denominator. And so we know if we want to differentiate that using the substitution method, well, we need to have its its derivative as part of the problem. Well, its derivative would be 5. That's not a problem. But what about the x squared? The x squared is there. And because it's not related to the derivative of this function or the function as a whole, that whole denominator, that x squared presents a problem. So just because we encounter an antiderivative that looks complicated does not mean it can't be solved. But once we break it down and think of it structurally, what's really going on? What do we need in order to be able to use our standard integration techniques? Automatically we do have a problem here because we see a nested function where we might use substitution, but we also see something that's not related to it, something that's just extra, that's added on, and overall this antiderivative is now more complicated than the one we started with. So because this portion is now something that we don't really have a technique to solve, that means that this particular combination of u and dv is not going to be the one we want to use. So the original one, for sure, it looked complicated. And choosing one versus the other, choosing this particular value for dv, it looks originally like something that maybe we can't integrate. But don't forget that substitution is an option. Just because we can't directly use a sum and difference rule or a power rule, something like that, does not mean that it can't be integrated, because substitution opened up a lot of additional possibilities for us. So this, in fact, can be integrated using substitution, and using our integration by parts formula, combining our different components together, we actually ended up with a new integral that we could solve, again using substitution. So we actually use substitution twice here, and that unfortunately is going to be realistic. We will encounter problems where it is layered. We do have to do layers of substitution, maybe embedded in an integration by parts problem. Unfortunately, it's realistic. There's no shortcuts. There's no way to simplify something past this. But the good news is this pairing was doable. It did work, so that would be the pairing we would want to use for this particular antiderivative. Okay, so let's wrap it up with a definite integral. So we looked at a definite integral when we did substitution as well. And the general idea with substitution is when we change the variables, we have to keep in mind that our limits of integration only apply to the original variable. So we have to make sure we change back before we apply our limits of integration. So here, as long as we don't use substitution, we're going to maintain the same variables throughout the problem. U and V are just temporary constructs in order to figure out how the derivatives and antiderivatives are going to fit together using the integration by parts formula. But we don't actually change any variables when we use integration by parts. So more than likely, those limits of integration will continue to apply throughout the duration of the problem. But in general, we just wait until we've integrated, and then at the very end, we substitute our limits of integration. Okay, so we have a product of two functions. We have x cubed times the natural log of x. Okay, so we want to integrate by parts, knowing that this is a product, and maybe it resulted from differentiation via the product rule. And so using what we know about the product rule plus our integration by parts formula, we may be able to break this down, reconstruct this as a function, and then a function times dx, something like that, and combine different components together to create a simpler integral from this more complicated integral. Okay, so remember, our u needs to be something we can differentiate, and our v needs to be something, or excuse me, our dv needs to be something that we can integrate. Now, as soon as I see the natural log function, I know I'm kind of limited as to what I can do there. Natural log is not something that we have a direct antiderivative for. So I cannot choose natural log to be something associated with dv, because natural log is not something that I can directly integrate. So automatically, that means we're going to choose natural log as our value for u, because this is a function we can differentiate, even if we can't integrate it. And then dv, we'll choose dv, at least for our first try, to take on the value of the remaining function of x times our differential dx. So we have our u, we have our dv, we have u, we need v from integrating, and we need du from differentiating. So I'm going to take my derivative, so du dx is going to be 1 over x. So that means du is going to be 1 over x dx. Okay, and then we're going to integrate our choice of dv in order to get v. So v is going to be the antiderivative of x cubed with respect to x. And we can use our power rule. So increase the exponent, divide by the new exponent. So that's going to be 1/4 times x to the 4th. So we have u, du, dv, and v. So now we can substitute into our integration by parts formula. And as long as we end up with an integral that we can directly solve, either just using basic integrations formulas or using substitution, then we know that this was a correct pairing. So u is natural log of x, and v is 1/4 times x to the 4th. I'm going to put my 1/4 x to the 4th first, and then I'll put my natural log of x. Okay, minus v du, integral of v du. So v and then du. So v is going to be 1/4 x to the 4th. And then du is going to be 1 over x dx. Now we've encountered a problem kind of similar to this one before. That's a good indication. So notice we just have terms involving x. We don't have any nested functions. We have x on top, we have x on the bottom, which means we're going to have something that simplifies and cancels out. So let's simplify down what's left as that integrand, and then we'll see if we can integrate from there. So we have 1/4 times x to the 4th times the natural log of x, minus, we have a coefficient of 1/4, and we can pull that out if we want, or we can leave it inside if we want. But more importantly, we have an x to the 4th, which would be in the numerator, divided by x. So when we cancel out, that's going to leave us with x cubed, and we're differentiating or anti-differentiating with respect to x. So this is now an antiderivative we can find directly just using the power rule. So that is good news. So once we evaluate that, then we're good to go. So we have 1/4 x to the 4th times the natural log of x. And then for this one, we're going to increase our exponent by 1, so it becomes a 4th power, and then divide by that 4th power. So that's just going to take it to the denominator. And so our new denominator is going to become 1/4 times 4, which is 16. Where's our plus c? Well, remember, this is a definite integral. We don't need plus c. So once we get down to our final answer here, we're now evaluating this from 1 to 2. Now, where are we plugging in the 1 and the 2? We need to be careful here. So originally, it might seem like maybe we're only plugging in right here, since this was the actual integral that we evaluated once we used the integration by parts formula. But remember, when we're using the formula, we're using the formula to take an antiderivative and then evaluate from 1 to 2, and this entire integral evaluated using the formula we have on the right-hand side. So even though we don't see any type of integration involved with u and v, this is part of the formula used to evaluate this whole integral. So that means the limits of integration, whatever they happen to be, are going to apply to every single part of this problem when we use the formula, because both terms over here are being used to generate this antiderivative that we were attempting to find using this integration by parts formula. So we have to plug in our limits of integration to both terms. And of course, it's going to get relatively complicated, but we have the calculator. So when in doubt, just use the calculator to evaluate. So we're going to plug in our upper limit of 2. I'm going to put brackets around everything so we can keep things grouped appropriately. So we have 1/4 times 2 to the 4th power times the natural log of 2 minus 1/16 times 2 to the 4th power. And then we're evaluating the same expression with an input of 1. So 1/4 times 1 to the 4th times the natural log of 1 minus 1/16 times 1 to the 4th. So whatever all of this simplifies down to, that will be the value of our integral. Okay, now first off, natural log of 2, that's going to be an irrational number. So what were our directions with respect to the answer? We want the exact answer, and we also want an answer rounded to 2 decimal places. But for now, I'm going to pay attention to the fact that we want an exact answer. Because natural log of 2 is an irrational number, if you were to type this into your calculator, all you get is an approximation, not an exact value. So we're actually going to leave natural log of 2 alone. Now, natural log of 1, that's a different story. If you evaluate the natural log of 1, it actually comes out to 0. So natural log of 1 times the other factors in this term, well, if this goes out to 0, then this whole term is also just 0. So that term comes out to 0. It's eliminated. So then it's just a matter of evaluating the rational parts and simplifying things down as far as we can. So we have 1/4 times 2 to the 4th power. And that's going to come out to 4. Okay, so now be careful, don't forget the natural log of 2. So the coefficient, it's going to be 4 times the natural log of 2. And that's just a number. Natural log of 2 is just a number. It just happens to be an irrational number. And then 1/16 times 2 to the 4th power. So 1/16 times 2 raised to the 4th power. It's going to come out to 1. So minus 1. And then we know this came out to 0. And so we are then subtracting negative 1/16 times 1 to the 4th. Okay, well 1 to the 4th is just 1, right? So negative 1/16 times 1, which is just negative 1/16, and then that's subtracted. So those two negatives turn into a positive, and so it's going to be plus 1 over 16. And so if we clean that up just a little bit more, these are now like terms. They can combine. So we have negative 1 plus 1 over 16. And that's going to give us negative 15 over 16. Not surprising. So if we think of this as negative 16 over 16 plus 1 over 16, that's going to be negative 15 over 16. So our exact answer would be 4 times the natural log of 2 minus 15 over 16. The only other way we might rewrite this in a different exact form is maybe getting a common denominator. So if we multiply it on top and bottom by a 16 for our first term, we could get a common denominator. But because these are constants, I wouldn't say that that's really necessary. And of course, then we can get an approximation, and we want to round to 2 decimal places. So 4 times the natural log of 2, well, that's where we suddenly encounter that irrational number, minus 15 over 16 into 2 decimal places, that's approximately 1.84. So that concludes our discussion of integration by parts. Integration by substitution, integration by parts, both really important techniques to help us solve antiderivative problems where the rules, maybe the power rule, the sum and difference rule, they just don't apply directly. So keep in mind, integration is fundamentally more challenging than differentiation. So if you looked at these problems and thought, well, the chain rule, the product rule, the quotient rule, they were complicated, but they were nothing compared to this. It's true. Anti-differentiation integration automatically is more challenging. There are certain integration problems that we can't actually solve by hand, that we don't actually have a technique to solve by hand. They can be solved using computers, but substitution, integration by parts, regardless of how versatile they are, there will be certain situations that they just don't work for. They do open up the door to a lot of additional possibilities for us, but these are not going to be exhaustive techniques that cover any function that we'll encounter. So keep that in mind. And just to reiterate, with integration by parts, don't be afraid to engage in some trial and error in terms of determining how to structure your different parts in the integration by parts formulas. Trial and error is necessary sometimes. Sometimes you may pick a pair that works. Sometimes you may start with a pair that doesn't work. That's okay. If you find one where your integral just becomes more complicated, just start over, try again, pick a different pair, and you'll eventually find the right pairing.